I'm going to do a little review of special relativity, which we did last time. Okay, we've been doing it for the last couple of weeks. Okay, we talked about the fact that we have length contraction and mass increase and time dilation, all that good stuff from special relativity. Is any of that stuff from special relativity? Is that does that have anything to do with science? Does that have anything at all to do with physics? Let's find out. Okay, here's I'll start with my universal movie. Okay, and universal movie again is a tool that I use. I recommend it to everybody. And what it is snapshots. You had these motion pictures, especially when you had in the 1920s and so on. One frame at a time, went through the lens, and so if you just looked at one frame, well, there's nothing moving inside the frame. If you want to see something moving, motion picture, well, you had to have the whole reel go through the lens, right, so that it's shown on the screen. And so the question is, when you look at a single frame of the film, nothing is moving in there. That's more or less what we're talking about when we say the universal movie. We're going to treat it as a movie. You can call it a three-dimensional movie. You can say it's God's movie. Okay, so God has filmed the movie. Now he's got the film there, a three-dimensional film, and so he's got all this. You look at any given frame, and everything is just static. Nothing is moving. He just took pictures, of what was happening in the universe. And what you see in one frame is just all the atoms just in one location. You'll see all the planets in one location. You'll see that every star and galaxy, everything is a given location. Okay, nothing's moving in that frame. And in order to see something moving, you have to go to at least two frames. Okay, so we have the universal movie, single frame, nothing is moving, and within that you have only static concepts. You have all the objects, you have location, you have distance, existence. That's all in a single frame. You don't need motion for any of those concepts. On the other hand, if you want to have motion, you want to have time, well, you got to go at least to two frames. In other words, you have to have the film rolling along. Okay, and that's more or less the notion behind the universal movie. And here you see it. Okay, here's the frames of the film. You have the static concepts at the top and the dynamic ones at the bottom. You can see the ones on the top, the yellow region there, it only points to a single frame. The beige one at the bottom points to at least two frames, and you can put more if you want, but at least two frames is the minimum to create all these dynamic concepts such as motion and time and energy and so on. Okay, why is length and mass, which is what we've been covering, why are those static concepts? Well, we look at the definitions, and here are the definitions of physics. Okay, what is length? Continuous matter between two surfaces. What is mass? Number of atoms. Okay, quantity of material, matter. That's what mass is. And I just want to point out that not only time is a dynamic concept, which is down there at the bottom right, okay, which is time dilation. So you can't put it in there with length and mass, but you've got inertia. And I just want you to keep in mind inertia, which is resistance to motion. Okay, in other words, a force comes against you and you push in the opposite direction to that force. That's called inertia. It's a resistance to change, right? And so inertia is a dynamic concept. Inertia is not a synonym of mass because mass is quantity of matter. Okay, so keep that in mind. Okay, we have a contradiction because they define mass as inertia, and no, they are two different things. If you're going to talk about inertia, you can say almost is the opposite of weight, okay, because you have something weighing down or sideways, right, or pushing in a given direction, right, and something that opposes it, which could be the atoms that make up the thing that you're weighing, right, or it could be something that is preventing that thing from moving. Like, you can put a box on a table, and the inertia of that is zero, really, because it's not moving at all, okay, unless a force acts upon it, right? So just keep that in mind. Mass, did it lose its mass? Is mass zero because inertia is zero? Okay, keep that in mind. Okay, so here we have good old Stevie Hawking. Okay, he died a few years ago. And he wrote in his Brief History of Time, you'll find this in the glossary, okay? Mass, the quantity of matter in a body, its inertia, or resistance to acceleration. Well, quantity of matter, like if you have 10 marbles in a bag, there's only 10 marbles in there. That's quantity of matter. If you look at every marble as, a piece of matter, as a unit of matter. So you got 10 marbles in there. Do we need to know? Do we need to measure? Do we need to count them? No, we don't. Mother Nature knows there's only 10 in that bag. Before you count them, before you measure, before you do anything, there's already 10 in that bag. You can later on count them and say, oh, I counted them and found out that there's 10. Mother Nature already knew that. God already knew that. The devil already knew that. All these guys up there whom we pray to every day, they already knew how many marbles are. It's a fact. It's a question of existence. There exists 10 marbles in there, whether you count them or not. Okay? This is not a Schrodinger cat kind of thing where the cat is dead and alive at the same time. No, God knows whether the cat is dead or alive before you look. Okay, so just keep that in mind. One thing is existence and what is, and the other one is measurement of what you perceive or what you measured or what you understood. Maybe you're drunk and you don't even know what you're looking at. So it doesn't matter what you concluded. What matters is what is, independent of your conclusion. And so here we have mass, quantity of matter, a contradiction because quantity of matter does not match inertia, which is resistance to acceleration. Okay, weight, the force exerted on a body by a gravitational field, it is proportional to, but not the same, it's its mass. Right, of course, because weight is inertia, or you could say it's the opposite of inertia. Weight is what goes down, and inertia is what tries to prevent weight from going down. So it's kind of like an antonym of weight. That's what inertia is. Okay, so yeah, if you try to cover all the bases like Hawking did there, and here you have a PhD, many years in the industry, theoretical physicist, mathematician, right? Yeah, you don't define terms precisely. Why? Because you can get away with murder. If you define that word in two different ways and you say, look, it's a quantity of matter and it's also inertia. Well, which is it? I mean, those two are not synonyms. Quantity of matter is not inertia. Okay. Here we have situation. The fellow says, the following says, well, this was from Quora, okay, and I like what this person said, so I thought I'd put this up there. Many people think inertia is mass. Others think it is momentum, depends on the object's mass and speed, while others think it is a force. This guy says he's a physicist, okay? It is not a quantity, inertia, right? Even the vague idea is not well defined in physics. Absolutely. They don't define these terms because if they did, they would be in sorry shape. It is best not to add to the confusion. Don't use the word. There is absolutely no need for it. There is no bit of physics which requires the use of inertia. In most cases, a better word like mass does the job. Okay? And yeah, there you have mass, has 1 trillion hydrogen atoms. That's what that box has. And its inertia, I guess, is 0 because it's not moving anywhere. Okay, so what is its inertia? So yeah, you can't say mass is inertia. Absolutely not, because inertia is really related to motion, whereas mass is not. Mass is quantity of matter. And if you want to define it otherwise, then you can't define it as quantity of matter, and we have a contradiction. What are we going to call quantity of matter then? You know, when we say that we take the grand kilo from France, you know, the one that used to be the standard for mass, and we take it to the moon, it weighs less. And people say, well, its weight changed, but not its mass. And so what are we referring to when we say that its mass did not change? Well, we're saying its quantity of matter did not change. What changes its attraction to the center of the object, the celestial object. That's what changed. But the mass did not change. What do they mean by that? Quantity of matter. So then don't say what's its inertia. No, inertia is weight in a different it's a different way of rephrasing weight. That's all it is. It's the opposite of weight, so to speak, like an antonym. Okay, so what are the conclusions that we have from special relativity from the last couple of weeks? A prediction is not a theory. Okay, and we had that with our science critic, and we finished with him because there's nothing more to address. I think we addressed every issue that he raised. Okay, so we're not going to have this fellow on here, at least not for now. A prediction is just a description. You know, if you say that something's going to happen tomorrow, so far you haven't told us why. You haven't given us an explanation, a cause or a mechanism. Oh, you said it's going to happen. Okay? You said, my horse is going to win tomorrow at the race. That's a prediction. Okay? You haven't explained why he's going to win. Okay? An explanation is a theory. Okay? So remember, if you explain something, now we have a theory. The theory of special relativity, SR, right, is not a theory, but a description. Okay? It's not, there's no explanation in special relativity. Okay? Special relativity predicts that an object traveling at near sea will shorten in the direction of travel, gain weight, and waste your time. That's what special relativity is in a nutshell. SR, special relativity, does not explain the physical mechanism underlying these events, these phenomena. Okay? They don't explain that. They just say it's going to happen. We measured it. Here are the numbers. Okay, you told us that it's going to shrink, but you haven't told us why. What physically is happening in there? That's what we need. That's an explanation. That's a theory. Okay, and it says the icing on the cake is that special relativity denies that these phenomena are real. Why? Because they say that in your proper location, right? Proper length, proper mass, proper time, that's the one the guy's carrying with him. The watch that you're carrying, that's proper time. The ruler you're carrying, that's proper length. And the mass, whatever, the grand kilo that's close to you, that's got a given mass. So what is it about? It's about the guy far away who's measuring all this stuff. So it's about measurement, not about what is. Okay? What is proper, and proper has not changed, they say. So if it has not changed, who cares? You could be drunk for all I care, measuring from afar, and that changes nothing. Existence has nothing to do with special relativity. Cleans its nose holes with it, because special relativity says from afar we're going to measure, and we're going to measure differently than the guy who is close to the object, okay? Which is called the proper length, proper mass, proper time. And so if for him the time doesn't change, then that's the real time. That's the one Mother Nature blesses, not what the guy measured out there. We don't care what he measured. Okay, that's what special relativity is about. And again, if they say it's real, which they don't, because they say in its proper frame of reference, nothing changed. Okay, so they do concede that, so nothing changed. And it's a question of measurement. Who cares about that? If you measured wrong or you measured something with a wrong device, who cares? Measurement means that you're wrong. You just got to correct the device you use to measure. That's all it means. So, it says special relativity is strictly an issue of measurement and therefore no concern whatsoever to physics or science. Okay, it's an issue of measurement. And we don't care about that. That some concerns the mathematicians, They want to play around with the fact that something measured differently. Okay, fine. Joey measured one thing, Johnny measures something else. Who cares, Who is correct? Well, correct is the guy who matches Mother Nature. Okay, if there's 10 marbles in the bag, and that's a unit of measure, we have 10. And the guy can travel at the speed of light. He can go do whatever he wants. There's still going to be 10 in there. Okay, nothing's going to change. Okay, and so don't tell me that the mass increased, that now we have more marbles because you traveled at the speed of light. I'd like to have whatever he had. I want to travel at the speed of light too. Okay, so here we have some authority. Okay, Fermilab. We have Don Lincoln. He's a fellow who does physics. Physics, mathematics. That's what he does. He just tries to explain um, what the mathematicians do or what they believe in, what this religion is all about. Okay, and here it is. And yeah, he's a caricature of a physicist, and he says relativity has been thoroughly tested, and there is no credible criticism of the theory. And he's so gullible, he just accepts all this stuff at face value. It's just like he just memorized it in school or something. And he just spits it out. Okay, so they just say, look, it's a fact. We've proven it. Well, this is what we believe in, and we believe the ruler shortened in one direction, gained weight, and time was wasted. That's what they come down to. But he does say one thing, which is a historical thing. Okay, here it is. He says, relativity key concept, Lorentz gamma. Right. Okay, so the Lorentz gamma is the key concept in special relativity. And I went over that a couple weeks ago, somewhat not very important for science or physics. That's why we don't dwell on that nonsense. It's an equation. That's what it is. And the question here that I'm going to raise is not that it has any validity or any importance, really. Validity, we don't care, but it has no importance in science or physics. Okay, it's got to do with mathematics, with them using that to say, oh, length contracted, mass increased, time dilated. Okay, what I want to show is that it wasn't Einstein, who came up with any of that. Okay, and here you have a little bit of history in a chart. Okay, how this equation, which you see it there, Lorentz factor. Okay, that's the gamma that they were talking about, that Fermilab was talking about. In 1887, we have Michelson and Morley, and what they did was they ran a series of experiments. This was, I guess, the most important one, where they wrote their paper. And they said, look, there's no ether. Everybody believed until then that there's all these particles out there filling the vacuum space, right? And that the movement of these particles is what light is, the vibration of these particles, okay? And about a year later, all these people, Heaviside, Fitzgerald, and Lorentz, all these people believed in the ether, and they were a little upset that at the results. And so they tried to explain the Michelson-Morley experiment, and they said, look, let's not abandon the ether. We just have to explain it. Okay, and so Heaviside, he had worked with what he called charges, electrons, and he wrote a paper where he said, look, in the direction of travel, the electron flattens out. So that was the length contraction. And Fitzgerald heard about that. And he said, oh, we can apply that to light as well. So maybe the photon of light, or whatever light is, maybe the wave, flattens out in the direction of travel. And so he wrote first to a magazine, I think to Science Magazine, or one of those important ones. And then he wrote a paper. By the time you get 3 years later to Lorentz, he comes in there and he comes up with this Lorentz factor, which again, the crucial factor is that 1 minus v squared over c squared, velocity of the object over velocity of light, right? Squared. And this had already been coming through, there were lots of mathematicians that had already worked with that relation. But today we give credit to Lorentz, okay, and say, okay, he came up with the gamma factor, and this is the one they're going to use to multiply and divide and to show that time dilates and mass increases and length contracts. And one of the guys who did a lot of that work was Poincaré. He was a French guy. And you can see how old Einstein was in all those years. He was 8 years old in the days of Michelson-Morley, 9 years old when Heaviside wrote his paper, his paper really, because he did write a paper. And Fitzgerald, he was 10 years old when Fitzgerald proposes it to explain the ether. Lorentz, Einstein was, 13 years old? And then finally, he took the credit for discovering special relativity. Nobody knows any of these other guys. Everybody just knows Einstein. Okay, he's given the credit for all of it today. And I just want to point out that that is not the case. In fact, here you'll look it up in the Wikipedia. Okay, this is a list of all the people who worked, all the mathematicians, right, that worked on the Lorentz factor. Okay, and there's a few of them there. Okay, so you can look this up. Okay, it's all those people who contributed to the notion of this Lorentz factor until they finally zeroed in 1892 on this gamma factor, which is what they use to explain the measurements, right? That's how it works. Okay, they still haven't explained the physical cause, okay, and that's why it's not a theory. All they're saying is, look, if you put this factor in there, that's what it'll do to the equation. Okay, that explains the equation. It doesn't explain what happened to the object, why it increased in mass, why it time dilated, and why length contracted. Okay, what we want to know is the physical mechanism that causes an object to do all these things when it travels close to the speed of light. That explanation, that theory is not, you'll never find it in special relativity. Okay, there's no explanation. Okay, and what's interesting about all that is that Einstein, even today, is credited with having gotten rid of the ether. They say that's what was different. That's what his contribution was to length contraction and the Lorentz factor and all this stuff, special relativity. His stuff was getting rid of the ether. Not true. Okay, here's Einstein, 1920. And we're talking 1908 is when special relativity is given birth. You could say even 1905 with the mass paper that Einstein wrote. Okay, that's another way of looking at it. You can also look at it from Poincaré's work, which preceded Einstein's. Okay, and this is what Einstein says in 1920, several years later. He says, we may say that according to the general theory of relativity, and remember, special relativity is a special case of general relativity where there is no gravity. It's flat land, essentially. You can't fall down in flat land. That's special relativity. What they've done is taken away gravity. But it's a special case of general relativity. That's why it's called general, and the other one's called special, right? We may say that according to the general theory of relativity, space is endowed with physical qualities. So he says space is physical. That's what Einstein was saying in 1920. In this sense, therefore, there exists an ether. So he's saying that space is filled with ether. There is all these bunch of particles in there. Some say it's moving, some say it's static. They have all these versions, right? But ether is a bunch of particles. That's all it is. Many particles. And just in case, many particles does not an object make. Okay? A tree is an object. Okay? A child is an object. Forest is not an object. Okay? Forest is many trees. Children is many many childs. Okay? So according to the general theory of relativity, space without an ether is unthinkable. Okay? So Einstein did not get rid of the ether. What he contributed was his name. That's all he did. He put his name on special relativity, took the credit for all of it. Okay, and what is interesting is that he eventually ended up in Princeton at the advanced studies there in Princeton. That's where he worked the last few years of his life. And here he confesses what happened in the last 6 years of his life, 7 years of his life. And what did he conclude? He concluded he knows nothing, that he's an ignorant individual, that his life was wasted. Okay, and this is what Einstein says. Okay, he says, I'm generally regarded as a sort of petrified object, rendered blind and deaf by the years. People were laughing at him because he did not believe in quantum, specifically. I have become an obstinate heretic in the eyes of my colleagues. And then he says, all these 50 years of conscious brooding have brought me no nearer to the answer to the question, what are light quanta? Nowadays, every Tom, Dick, and Harry thinks he knows it, but he is mistaken. I consider it quite possible that physics cannot be based on the field concept. What did Einstein come up with? The field equation, right? In other words, on continuous structures, in that case, nothing remains of my entire castle in the air, gravitation theory included, and of the rest of modern physics. Yeah, Einstein died an ignorant man. He died disillusioned. He could never figure out how this universe works at all. And so he became an atheist in his own religion. Here's the pastor, here's the Pope of general relativity and special relativity. He took the credit for that as well. And turns out he dies saying, I became an atheist in my own religion. I don't believe in it. That's how messed up all the mathematicians that picked up on what Einstein, the foundations he laid. They picked up on that, distorted it so much that Einstein said, you guys are all crazy. And so they said, well, you're too old. They didn't say he was crazy, they just said he was old. And so it's interesting that you have people like Don Lincoln who worship. In fact, everybody out there worships Einstein. Here we have another YouTuber who tries to worship and raise the value of Einstein, through her Pope, her hero. Okay, and this is Feathers. Okay, and she's got this little Einstein there. It says, "I'm all shook up." Well, we need Elvis here to put some music behind that. Okay. So yeah, Einstein died an ignorant man. He never discovered anything. He didn't, all he did was mislead a generation, full 100 years of it, of mathematicians, down the wrong path. That's all Einstein contributed to so-called science, to physics. In other words, nothing. You could say he contributed negative knowledge, negative information, negative explanations, because all the explanations we have today from mathematical physics for all invisible, intangible objects out there that mediate, how these phenomena work, is all irrational. Not one, okay, out of mathematical physics passes the rationality test.